So we are going to look at implicit differentiation. Implicit differentiation refers to when you have more than one variable that you're needing to differentiate, whatever that may be. Now you've seen x's and y's, okay? We're going to still have some x's and y's, but we're also going to throw in a's, b's, c's, whatever variable we want, okay? So we're talking about a couple different rates. And here's what you're used to. If I said y equals, and let's just go 3x to the fourth. Some basic derivative here. Okay. And so our derivative would be y prime equals 12 x cubed times 1. Everybody agree with that? Mm-hmm. Okay, where'd the 1 come from?
The inside piece.
Okay, the inside piece. There's that chain rule. Right? Pretty basic derivative, right? We don't really need the 1, but we need to make sure we're understanding to look back inside. Okay? We could also write it like this. dy dx equals 12x cubed. And then again, still times 1. Okay there? Different notation. So y prime, derivative of y, still means derivative of y with respect to x, because x is my variable inside. We can also write it like this. Okay? This is a little bit more of that implicit format because I took that derivative of y. Now, what we need to realize is when you do something to an equation, your old rule, what you do to one side, you do to the other side, right? Everybody agree with that?
Yeah.
Okay, so, if I said that y equaled 2x, what would the derivative be? 2, just 2, right? Everybody agree with that? Okay. Technically, it's this. dy dx, I took the derivative of y with respect to x on the left side equals 2 dx dx. I took the derivative of x with respect to x on the right side. Now, what would dx over dx equal? 1. So it's still going to be a 2, right? But we need to understand we took the derivative of y with respect to x, and then we took the derivative of x with respect to x. And I know that cancels to just a 1, so the derivative is just 2, but we need to understand sometimes those variables aren't going to cancel for us. It's still looking back at the inside. I'm checking that inside piece. Implicit differentiation is generally used when cannot solve for variable. So, these two original nice simple derivatives, they're already solved for y. Okay? And I've got y's up there, but you've seen f of x equals, g of x equals, whatever, it's solved for that variable. That's the nice thing. Okay? Let's look at something like this. Let's say we have x squared y plus 2y cubed equals 3x plus 2y. And I said find dy dx of that. Now what makes this so difficult is the simple fact that y is not alone. It's not y equals. If it was y equals, and I know these are basic ones over here, but even if I can make it a much longer one. And that's not a difficult derivative either. Nice to solve for y. Even if we threw a trig function in there, it's not the worst thing. We come up with those values. Now I look at the equation I'm given. It's not solved for y. And in this case, I cannot solve it for y. There's no way I'm going to get y alone because I've got differing powers here. Now, if they were all the same power, you can get them all on one side, factor the y out, or y squared out, or y cubed, whatever it is. But they're not the same power, so I'm not going to be able to get that y isolated. Pretty okay with that?
Yeah.
Now, this means you're actually looking at something that's not a function. In other words, it doesn't pass that vertical line test. So for every x doesn't correspond to just one y, you could have an x value that corresponds to 3 y's. Pretty okay with that? Okay, now let's look at the derivative. This will be a product rule. So we're taking the derivative with respect to x. So all I'm doing is looking at this first part, x squared y. First, x squared. Derivative of y is 1 dy over dx. Taking the derivative with respect to x. Now I know I don't need the 1, I'm just reminding myself, hey, that's a 1. It's not going to change anything. Plus second y times derivative of the first 2x dx dx.
Wait. Not dividing them all together.
What's that?
Why? I'm sorry, it's just like looks weird to me, but it makes sense.
So first, derivative of the second, plus second, my y, derivative of the first 2x dx dx. Now, I know you really don't need the dx dx in there, but I would suggest on at least the first one in your notes you have it there so you can kind of see what's going on. Plus, now we're looking at this guy. That's a power rule. So there's no new rules here. Same power rule. 6y squared dy dx. So 3 came down. 3 times 2 is 6. Y squared, derivative of the inside, dy dx.
Wait, so what's the difference of dy, dx, dx? Like why are those different things like dy, dx? Like it, of course, like
Well, this is the derivative of y with respect to x, and this is the derivative of x with respect to x. 2 different variables.
Okay.
So what happens if you take the derivative of x with respect to y? Does that just change what you're taking the derivative of?
Yeah.
Okay.
That's all it does. Top letter is what you're taking the derivative of, bottom one's with respect to. Doesn't matter what the letters are.
So what's happening is pretty much like with dy over x, which means you're taking the derivative of the first one and you should keep the second one the same. Okay.
Why did you, for the first variable x squared, why didn't you switch it to 2x?
Because I did the product rule. Product rule is first, derivative of the second, plus second, derivative of the first.
Okay, that makes
Same old product rule. I'm not changing any of the rules. Right side. All right, now what would be the derivative of 3x? 3, and the derivative of the inside, dx dx. There's that chain piece. So those dy dx's or dx dx's, those are your chain pieces. What's the derivative of 2y? 2. Then the inside,
dy dx.
dy dx.
That's always over dx.
Because that's what we were asked to find, derivative with respect to x. We're looking for that derivative with respect to x, so that's why it's always over x. No tricks there. Now, the dy dx, the dx dx in the problem. This represents chain rule of inside. So inside's x, dx dx. Inside's y, dy dx. There's that chain rule where I'm looking back to the inside. You're already used to using the chain rule. Nothing new on that, just looking back to the inside. Now, I do realize that dx is 1. So in my notes, I go ahead and do that. I just need to understand that I was supposed to look back to the inside. No, it's not going to change anything, and I don't know what dx is, but I know dx is the same as dx. That's why it's 1. Nothing new on that part, whatever. If numerator and denominator are the same, you get a 1. Now, this says to find dy dx. That means I need all the dy dx's on the same side. So I'm just going to put them on the left side because 2 of them are already there. So I've got these 2 dy dx's on the left side. I'm going to bring this guy over to the left side. And that means this one here is going to the right side. Everybody okay with that? All right, so I'm going to leave the 1 out. That's not going to matter. X squared dy dx plus 6y squared dy dx minus 2 dy dx equals 3 minus 2xy. Now, looks like a mess, but keep in mind, if you're wanting to solve for a particular variable, and in this case dy dx, I need them all on the same side. So all I did was move all those terms with that variable on the same side and everything else to the other side. You have done that many, many times. Okay? You're just not used to seeing dy dx's all over the place. It's still the same variable. Is everyone okay with this step?
Yes.
So I'm going to do 2 steps in 1 here. I need dy dx alone. That means it's going to factor out, right? So if I factor it out in front, it would leave the x squared plus 6y squared minus 2. Everyone okay with that? Then we divide it over, right? So here comes that dy dx would equal 3 minus 2xy over x squared plus 6y squared minus 2. All right, now let's review here. What does 3 minus 2xy over x squared plus 6y squared minus 2 represent? Slope of what? Slope of the tangent line. Which one? All of them. Okay? Because that's still the derivative, right? And that was our definition of a derivative. Derivative represented the slope of the tangent line, every possible tangent line. If I wanted a specific one, I'd need an x value. Right? So in the past, you needed an x value to substitute in, and you could find the derivative at that point, or the slope of the tangent line at that point. Does that make sense to everyone? Okay. The only thing that's changed now is that if I want the slope of a tangent line at a particular point, I need both the x and the y value, because there's both variables in the derivative. So, that being said, now this is not the graph of that function. Okay, but just kind of picture a graph something like this. Obviously not a function, right? Everybody agree with that? So let's say this is x is 2, and I said find the derivative, find the slope of the tangent line at x equals 2. Well, I got a little bit of a problem here. There's 3 different slopes. So I'd also need the y value. I'd have to say find the slope of the tangent line at the point 2, 1. Okay, now I'm going to substitute a 2 for x, a 1 for y. I can get that slope. Everybody okay with that? When you're looking at something that's a function, hey, find the slope of the tangent line at 2. There's only 1 point. Right? That's why those derivatives only had x's in them. This is creating something that's not a function. Okay, Because you don't have every x corresponding to only one y. You've got 3 y's sitting there. Are you okay with that?
Yeah.
Now, if I didn't have the cube here, that would be a function. I know it doesn't look like 1, but I could actually solve it for y. And get y equals something without working with any powers. So I would only have the 1x value. That's what's happening here. We're ending up with derivatives of both x's and y's. This is that chain piece. You were already used to kind of using the chain piece. Because when I had y, and you went and found the derivative of y prime, you also saw that as dy dx. Technically, it was 1 dy dx. There's that chain piece in there. Are you okay there? Power rule, product rule, quotient rule, chain, none of those rules change. Nothing new on the rules. Even the trig rules. Here comes the trig one. I'll make this a number 2. Find dy dx of sine x squared plus y equals y squared times 3x plus 1. So this would be another implicit differentiation. You can tell you got that y squared sitting there.
Is there an easier way to write like dy dx? Is there like a variable that stands for it?
You can use y prime.
Okay.
The reason I don't is I start thinking those are y to the first. You will see the book do that. So if I were to write out this other one, instead of using dy dx, I did y prime. It would look like this.
You can see where you would mess that up.
And I know for me, my handwriting, I'm going to start making that y cubed. And it's not y cubed because that's y prime. So a lot of times in a textbook or something neatly typed, like even a test or sometimes a worksheet handout to you, a lot of times I'll have this in there because you can tell the distinction really well. Okay? So yeah, you can use the y prime notation versus the dy dx, but I would encourage you, at least on your notes, to put the dy dx so you can see what happened, so you don't have that confusion later. Okay? And I'm more speaking for myself because I know what I'd do probably on the next step if I'm in a hurry. I don't need a power 1, I just leave it off. Because if I glance quick, I'll think that's a 1 and not a prime. Something like that. So it really depends on how neat your writing is and things like that. Okay? But you can use that notation. There's nothing wrong with it. I just don't like using it for notes because you want to see specifically what it was. Okay. Trig function left side. Product rule right side. Go left first. What's the derivative of the sine?
Cosine.
Cosine. So we're going to start with cosine. X squared plus y. Then the derivative of the inside. So now we're just looking on this inside. X squared is 2x. Y is dy dx. And I know technically x squared is 2x dx dx.
Wait.
We saw how they canceled out.
Oh, so because y would just be 1.
1 dy dx.
Okay.
Equals the other side product rule.
Wouldn't it just be easier to distribute the y squared out?
You're still going to do a product rule.
Yep.
So y squared first, derivative of the second is 3, plus second, 3x plus 1, derivative of the first, 2y, dy dx. So again, first, derivative of the second is 3, or I guess 3 dx dx. Second, derivative of the first, 2y dy dx. Question was, yes, hey, can you multiply this out first, distribute this first? You sure can, but you're going to have a 3xy squared. You're not going to avoid a product rule. Whether or not it works out easier, I don't know without doing it, but I'm still going to be doing that product rule. It's not going to change my rule. If it was something that would change my rule, then I would probably distribute it out so I don't have to worry about it. Something like that, but I'm not going to end up in that situation there. All right. Okay, now we've got to find dy dx. And first off, we've got kind of a mess here. I've got a cosine type with these two. This is pretty easy here, 3y squared. It's not bad. And then this guy's tied with these two. So now I would probably just distribute it. So we need to separate this out so then I can get the dy dx's alone. So again, I know it looks like a mess with that cosine there, but this is one whole term outside times the 2x and times the dy dx. Okay? It's a distributive property. Here's a 2y dy dx times the 1 times the 3x. It's a basic distributive property. You're just not used to seeing one where you have a larger piece out in front, something like that. Right? But when I draw it like that with the green and look at the arrows, you should recognize that distributive property pretty quick there. Okay? You've seen a lot of things in here so far that are really representative of what you've done before. They're just very different looks. That's what we got to work on getting used to. So here's my distributive property. I'm going to have 2x cosine x squared plus y. This times the 2x plus cosine x squared plus y dy dx. And it does not matter if you put the dy dx at the front or the back. I'm just used to putting it at the back. So I distributed the cosine. Right side, first term's easy, 3y squared. Nothing really going on there. Second part, there's my distributive property. I'm going to take 3x times the 2y dy dx, then the 1 times it. So we're going to have 6 plus 6xy dy dx plus 1 times 2y is just 2y dy dx. Okay there?
Yes.
We get a lot of stuff going on, and that's where we make some of our careless mistakes. But look at the process. Same derivative process, product rule, same old distributive process. Yeah, it looks worse. Everything's spread out. All right, I'm solving for dy dx. That means I need them all on the same side. You want them on the left side or the right side?
Left side.
Left side, okay, so that means that I'm going to pull this 6xy and 2y over. And I'm going to send this first cosine to the right side.
Yeah.
Everybody okay with that?
Yep.
Okay, so cosine x squared plus y dy dx minus 6xy dy dx minus 2y dy dx equals 3y squared minus 2x cosine x squared plus y. As you're writing that down, a lot of writing, a lot of stuff going on. Pretty basic concept. Hey, I need all my like terms, the one I'm solving for, dy dx on the same side. I just get them all on one side, move everything else to the other side. The biggest difference between this and solving some old equations you've had is in the past you had stuff that just combined and it kind of reduced down. I don't have any like terms to put together here, but I can still put stuff on one side and everything else to the other side. Pretty okay there? Okay, 2 steps in 1 here. That left side, we can see a dy dx in each one, so we picture that being factored out. Everything else to divide over. So if I had, that would give me dy dx, here a little bit, dy dx equals 3y squared minus 2x cosine x squared plus y, all over cosine x squared plus y minus 6xy minus 2y. And again, the only reason the derivative just looks really ugly is because you didn't have any like terms to go through and combine. It's everything just being carried along. Are they okay there? All right. Well, this guy. Let's write it as find slope of tangent line to x squared plus y squared equals 5x plus 4y at the point 5, 4. All right, now let's kind of investigate these instructions here as you're getting that down. Find the slope of the tangent line. What's that mean to us? Find the derivative. So we're going to find the derivative, which means we're going to find dy dx. Okay. And then we're going to find it at a particular point, 5, 4. You can't use your calculator on this because that dealt with functions. This isn't a function. All right, so that's one of the reasons why we practice finding a derivative and putting a value in first by hand. We know how to do that. So we're going to find the derivative and put the point in. Question?
Would we ever see a time where we'd be trying to find dx over dy?
Sure. Not today.
Okay.
We're going to have d whatevers.
Okay.
Now, what I want you to do, find that derivative. So just write out the long form. Don't bother solving for dy dx. Just write out the long form. Practice using your implicit differentiation. Then we're going to check that. Then we'll deal with the point and what have you. Again, don't solve anything. Just write out the long form. When you're done, look up here, check your work. Are you okay with that? All right, now we're trying to find a derivative at a point. So I have the point 5, 4. You have two choices here. You're going to have to find dy dx at 5, 4. So what we want is, I'm going to say looking for dy dx at 5, 4. And that's what this notation means. I'm looking for this guy at that point. For that piece. Your two choices are, one, you can solve for dy dx like we did in the last couple problems, and then put the 5 and 4 in. Or you can put the 5 and 4 in first, then solve for dy dx. Usually for me, I'll put the 5 and 4 in first because I can work the numbers faster than the letters. But I don't really think one way is easier than the other. You're still going to have to get dy dx along. So if I substitute the 5 and the 4 in, I would have 10 plus 8 dy dx equals 5 plus 4 dy dx. And I know there's a dy dx there, but think back to your basic equation solving. What if you solve 10 plus 8x equals 5 plus 4x? Get your like terms together and move. It's not that bad. So let's see, that would be 4. Dy dx is negative 5. So negative 5 fourths would be that slope or that rate of change. Everybody agree with that? So the question came up, well, we see dy other variables. Yeah, technically we already have a couple others. Remember, this was really 2x dx dx. And we're going to have dA dx, dA dt, dw dy. Okay. So remember, when we're talking about that, we're saying, hey, if I saw dA dt, this would be the derivative of a with respect to t. Everybody agree? Derivative of w with respect to t. Derivative of w with respect to y. Whatever the top one is with respect to the other. And that's going to, what's happening is we're working with multiple rates. And we'll start this in tomorrow's class, what we call relative rates. We're working with more than one rate there. We'll deal with those pieces. But anytime we're taking a derivative, it's a rate. Why is the derivative rate? Because it's a slope, which means it's a rate of change. Any type of rate of change. Does that make sense? Okay, so we've seen these instructions before, right? Nothing new. The only thing changed is now we have an x and a y we're having to put in instead of just an x. If I said find the equation of the tangent line, well, it would be y minus 4 equals negative 5/4 x minus 5. Same thing, right? The thing that got affected was the derivative. What if I said find the second derivative? What would you have to do first?
Find the first.
And the first derivative. Okay. So let's do this. I'm going to say find d2y over dx2 if x squared plus y squared equals 10. Now, you've seen second derivative notation a number of times, like f double prime, y double prime. You see the two apostrophes. Kind of had that there. You've seen this a couple of times, this second derivative notation, mainly in those last couple reviews or something. Okay, so we're getting some review of some of the notation. We're going to keep getting new notation as we go along. In our mind, we look at that, and that means second derivative. The reason the 2's inside on the top is because it's second derivative of y with respect to x. If you wrote them on both on the outside, it looked like the d's would cancel. That's why you get the different notation. So in other words, okay. Does that make sense? That's why the notation is a little bit different. So now we're looking at it going, all right, we can't cancel those. That means the second derivative. That's all it's referring to. So find the first derivative. I want the second derivative. So on your papers, find dy dx. This time you'll do your implicit and then solve for that dy dx. After you write out your derivative, you can look up and check. I haven't solved for dy dx, but I've at least got my long form sitting out there. And see if you agree with that for the derivative.
Wait. What do I have to do equals here?
Oh, derivative 10 is 0.
Oh.
Oh.
No new rules, zero constant 0.
Right.
Everybody okay with negative x over y? The 2's canceling out?
Yes.
Okay. So now we need the second derivative. So what rule do we use over there on that negative x over y? Quotient rule. Unless I bring it up, I'm just going to go with the way it's sitting. So now we'll go with that second derivative. All right, so this would be second derivative. d2y over dx2 equals bottom. Derivative of the top is -1 minus the top, negative x. Derivative of the bottom is dy dx all over the bottom squared. Now we got to simplify it, but long form. Make sure you're focused on that quotient rule. Bottom was y, derivative of the top is -1 minus the top, which is negative x, derivative of the bottom, dy dx over the bottom squared. Look like a regular quotient rule to you? These are one of those things that just really force you to stick to those rules. You know those rules, they're not changing, ever. So now let's look to simplify this. I'm just going to move right up here. Right? So d2y over dx2 would equal -y plus x times -x over y over y squared. Where did I get the -x over y from? That's what dy over dx is. I knew dy dx was -x over y, and so that's going in for dy dx. Again, a little confusing because you got a lot of stuff going on. But you see this dy dx right here. You took that derivative using the quotient rule. I'm just putting that part back in. Now let's simplify this. This would be -y minus x squared over y all over y squared. I can put that together, get rid of the parentheses at least. Look okay to everyone?
Yeah.
Okay, now I've got a complex fraction, so we'll multiply everything by y, which would give me -y squared minus x squared over y cubed. Y cubed, I wrote square, but I said cubed. So I did each piece by y to get rid of that fraction. Look okay to everyone? Good, so my final answer is -10 over y cubed. Think before you ask.
-10.
Oh, y squared. Because x squared plus y squared equals 10, so now x squared plus negative x squared is negative 10.
There you go. X squared plus y squared is 10. So a negative x squared minus y squared is -10. So it just ends up backs up. Now, it's not going to happen every time, but it did happen here. Okay. Now, would, for the second derivative, would this 1, 2, 3 all be correct?
Yes.
Yeah, just not simplified, right?
Yes.
We don't want to leave it here. We want to at least get the dy dx back in. Yeah. So any of those are correct. But I'll stress, same thing I've said before. You don't have to simplify, but you better know how. Here's one thing I would say. If you asked me to find the third derivative, I would much rather work with this guy than that one.
Agreed. Yes.
So simplifying does have its merits. Okay? There's always a time and place for it, but there's always a case where you better know how. Right? So I wanted to get this one up there because it kind of shows you some of this back substitution. I knew this guy right here. If I simplify down, it just ends up, wait, I can put the -10 in for that. All right. A little tricky, but pay attention. The biggest thing for you is you're so used to working things where like terms combine to get things together, and you take an equation like this, and it whittles all the way down to x equals 4. I mean, I can write a linear equation that parentheses and everything that spans all the way across the board. It's going to work its way all the way down to a nice simple little thing, right? Well, now these guys start like this and end like this because nothing combines a lot of times. Right? They end up staying roughly the same length because you just don't have terms combining. Right? Trust your derivative skills. Trust your problem-solving skills. In other words, trust your equation-solving skills. You know how to solve for something. Get it all on one side, everything else the other side. Trust those skills. You know how to do that stuff. That's not a big deal. Okay? You know how to back substitute when you see something. You know how to multiply everything by y to get rid of the complex fraction. Those are old things that you know. Maybe a little out of practice, but you know them. That's what you're going to focus on. Okay, homework. Let's see.